And you can see that r fourth time minus r square minus 4 pi square sigma square over omega square is equal to 0, which means r square is going to be dielectric constant square root of 16 pi square sigma square over omega square. This is the equations that you can get when we have some damping due to the electrical conductivity of the materials, right? Now, significance of gamma, the absorption index. I just suddenly give you that we can call this absorption index when the R refractive index becomes a complex number. The significance of absorption index is just electric field decay with the distance. A, that is the amplitude of the wave, and then I to the k star x minus omega t. That is the electric field in case of the complex number of the wavelengths, right? And then they can be separated in the real value and the imaginary values minus c omega gamma x, just like that. So this thing is going to be called damping, in other words attenuation factor of these wave equations, right? That has been something like decay of the waves, something like this. And then this decay can be called the attenuation factor, and then it has this mathematical form like that. And so that is the absorption index, the physical significance of the absorption index. Okay. Now we have another parameters which can be measured experimentally, and that is going to be called the absorption constant, alpha. Absorption constant. And there should be a relationship between the attenuation, the absorption index and the absorption constant. Now, the absorption constant is just a measure. We can measure experimentally, which is going to be e to the minus alpha x. In other words, if you have a materials with a thickness x, and then the incident beam intensity, and you measure the outcoming light beam intensity, and then you can equate that into this form, and that is the alpha is going to be called the absorption constant. So it is totally experimentally you can measure, right? And this experimentally measured absorption constant has to be related to the absorption index that we just talked about. Electromagnetic wave, that is light, right? Electromagnetic wave, the energy of electromagnetic wave, it can be defined as electric field and magnetic field current, right? Something like that. So that the intensity is going to be minus 2 omega gamma over Cx. Okay, the 2 comes from this attenuation factor is related to both of the fields there. So by curl those two things, then you end up with a 2. I write it here. Okay, so that alpha is going to be 2 omega gamma over C. If you compare those two things, you end up with something like this, right? So today we just discussed about the light wave, and we did not use F equal to m8 in the lattice wave case. We cannot use the Newtonian for the light wave because in the light we don't have a mass, right? So we use the Maxwell equations to get the equation formula, which is derivative of some partial differential equation in a form like that. In order to get that, we have to use the Maxwell equations 1, 2, 3, 4, and then we successfully get this kind of wave equations. And then in that wave equations, we found that the conductivity of the material is working as a damping. So when the conductivity is very small, like in the insulator, we do not have any damping, so that we have a non-dispersive system, which is a straight line, and the velocity is related to the square root of the dielectric constant of the material. But if it has some conductivity, like in semiconductors, in a metal, the sigma values are so large, and later you will find that in a metal, all the light is going to be reflected. That is a skin effect. So we just see, simply by looking at the material, we know that is metal or not, because of that the metal reflections, right? Metal texture. And in the semiconductor case, the sigma is considerable. And in that case, we all have absorption complex numbers of refractive index, and the absorption index of absorption and absorption constant, all those values coming from the attenuation factors, which originally come from the conductivity of the material. Next Monday, we are going to discuss about the matter wave. And in the discussion of matter wave, I recommend you to read the book first before the class. It's going to help a lot because it's a kind of a new ideas. All right? Any questions? Okay. The homeworks, did you collect the homeworks? Okay. Anybody who haven't submit the homework, he doesn't have to submit your homework later, because he has to submit the homework before the class. All right?